Somewhere in a laboratory in northeast China, a clear liquid sits inside a sealed chamber. A researcher applies pressure. Within seconds, tiny white crystals begin forming inside the liquid, and the chamber measurably warms. Then the pressure is released. The crystals vanish back into the solution almost as fast as they appeared, and the temperature inside that chamber drops by nearly 30 degrees Celsius in under 20 seconds. No compressor hums to life, no refrigerant gas hisses through a coil, no motor kicks on at all, and yet somewhere inside that small, sealed loop of salt water might be sitting the first real technical alternative to a machine that has cooled human homes in essentially the same mechanical form for almost 100 years. The compressor sitting behind your refrigerator right now has barely changed in principle since the 1930s. This might be the first thing in decades that genuinely threatens to replace it. Right now, refrigerators everywhere on Earth are running on a shared, almost century-old blueprint, and most people never think about it at all. A gas gets compressed, turns liquid, releases heat outside the fridge, then expands back into a gas inside it, pulling heat out of your food in the process over and over, thousands of times a day, for the entire life of the appliance. It works, it's reliable. It's also loud, mechanically complex, dependent on refrigerant chemicals that can leak and warm the atmosphere when they do, and increasingly expensive to run at the scale the modern world now demands. For 100 years, there hasn't been a serious mainstream alternative to that basic mechanical loop. That's the wall this new Chinese research is aimed directly at. This isn't a lab rumor or a speculative patent filing. The discovery was published in January 2026 in the journal Nature, one of the most rigorously peer-reviewed scientific journals in the world, by a research team led by Li Bing at the Institute of Metal Research, part of the Chinese Academy of Sciences. Nature doesn't publish claims on faith. Every result in that paper went through independent expert review before a single word of it reached the public, which is precisely the kind of scrutiny a claim this disruptive needs to survive before anyone takes it seriously. The Institute of Metal Research itself isn't some fringe outfit chasing headlines either. It's one of the oldest and most established materials science institutions in China, with a research history stretching back decades in exactly the kind of applied physics and chemistry this discovery draws on. To understand what Li Bing's team actually built, you don't need a chemistry degree, because you've probably already felt this exact effect with your own hands. Instant cold packs, the kind used for sports injuries, work by mixing water with a salt like ammonium nitrate inside a sealed pouch. The moment that salt dissolves into the water, the pack goes cold almost instantly, not because of any battery or mechanism, but because dissolving that particular salt actually pulls heat out of its surroundings to do it. That's the whole trick behind Li Bing's discovery too, just engineered into something reversible and controllable. His team worked with a different salt, ammonium thiocyanate, dissolved in water, and found that squeezing the solution under pressure forces the salt to crystallize back out, releasing heat as it does. Release that pressure, and the crystals redissolve, yanking a large amount of heat back out of the liquid in the process. Pressure on, heat out. Pressure off, cold in. That back and forth cycle, repeated over and over, is the entire engine. The analogy has a limit worth being clear about, because a one-time cold pack and a working refrigerator solve very different problems. Squeeze a cold pack once and it's done. The chemical reaction inside it runs its course and can't be reversed without opening it up and replacing what's inside. A refrigerator needs to do the opposite of that thousands of times a day, cycling the same cold and heat over and over without ever running out of material or needing to be refilled. That's exactly what makes Li Bing's version different from the pouch in a first aid kit. Because the ammonium thiocyanate crystals dissolve back into the same solution they came from every time the pressure releases, the whole cycle can, in principle, run indefinitely on the same sealed batch of liquid, pressurized and depressurized again and again. The way a compressor cycles refrigerant gas through the same closed loop today, here's the part that makes this genuinely different from other next-generation cooling research happening around the world. For years, scientists have been chasing what are called solid-state caloric materials, solid substances that heat up or cool down when you squeeze them or expose them to a magnetic field, specifically as a way to avoid the greenhouse gases and ozone-damaging chemicals used in traditional refrigerant gases. The problem with nearly all of those solid materials is almost embarrassingly basic. Solids are bad at transferring heat efficiently, especially at any real commercial scale. You can create a solid block that gets cold, but getting that cold reliably and quickly out of the block and into whatever you're actually trying to cool turns out to be a serious engineering headache, the kind that's kept these materials stuck in research labs for years despite genuinely promising lab results. Li Bing's breakthrough sidesteps that problem entirely by keeping everything in liquid form. A liquid can be pumped, circulated, and pressed against whatever needs cooling far, more efficiently than a solid block ever could. His team essentially merged the refrigerant and the heat transfer medium into a single fluid, doing both jobs at once. something solid-state materials have never been able to pull off. If you're the kind of person who appreciates an elegant fix to a problem that stumped an entire field, this next part is worth sticking around for because the numbers behind it are almost as surprising as the concept itself. So, to recap what's on the table so far. A team at a major Chinese research institute discovered that a specific dissolved salt, put under repeated pressure and release, can absorb and release large amounts of heat purely through chemistry. No compressor, no refrigerant gas, no moving mechanical parts required at all. That alone would be an interesting lab curiosity. What turns it into a serious contender is what happens when you look at the actual performance numbers behind it. At room temperature, the team measured the solution's temperature dropping by nearly 30 degrees Celsius within 20 seconds of depressurization, with even stronger cooling performance showing up at higher starting temperatures, exactly the conditions a real refrigeration system actually needs to handle. 30 degrees Celsius is roughly the difference between a scorching summer afternoon and a cool spring evening, and this system produces that entire swing inside a sealed chamber in less time than it takes to read the sentence out loud. Based on those measurements, the team's simulations calculated that a single full cycle of the system can absorb 67 joules of heat for every gram of solution used, while converting energy into cooling with roughly 77% efficiency. 77%. Most real-world mechanical systems lose a meaningful chunk of their input energy to friction, vibration, and waste heat long before that energy ever does useful cooling work. A liquid-based system with no moving mechanical parts to wear down or leak lubricant is, on paper, already outperforming the kind of losses compressors have lived with for a century. Now here's the part that connects this discovery to something much bigger than one lab result. Liebing's team isn't operating in isolation, chasing a novelty for its own sake. This sits inside a much larger, urgent push across Chinese research institutions to find an alternative to vapor compression cooling, the exact technology inside virtually every refrigerator, air conditioner, and cold storage warehouse on the planet today. Vapor compression cooling works by squeezing a refrigerant gas until it turns liquid and releases heat, then letting it expand back into a gas somewhere else, absorbing heat as it does, all driven by a mechanical compressor that runs almost constantly. It's a genuinely clever piece of engineering, refined over a century, and it's also the reason your refrigerator hums, vibrates slightly, and eventually needs its compressor replaced or its refrigerant topped up. According to figures cited alongside the study, vapor compression cooling alone accounts for roughly 2% of China's entire GDP and economic activity, while consuming close to 20% of the country's electricity and generating nearly 8% of its total carbon emissions. 20% of an entire national electricity grid dedicated to nothing more than moving heat from one place to another. That is not a rounding error in an energy budget. That is one of the largest single-line items in the entire system, and it's been running on essentially the same core mechanism since before most people's grandparents were born. That scale of energy demand isn't holding steady either, and this is where a second independent piece of research becomes relevant. A separate Chinese team, based at Huazhong University of Science and Technology, and led by researchers including Zhangjiang Duan, published work in the journal Joule describing an entirely different approach to compressor-free cooling, using what's called a thermogalvanic effect, essentially generating a cooling response through electrochemistry rather than pressure and dissolution. Different mechanism, different research group, same underlying goal, get rid of the compressor. That team has been explicit that they're developing multiple refrigerator prototypes and actively seeking industry partners to help commercialize the underlying electrochemical technology, a sign that this isn't purely academic curiosity on their end either. When two separate Chinese labs, working through completely different physical principles, arrive at the same conclusion within roughly a year of each other, that's not one team chasing a headline. That's a genuine, coordinated scientific direction, treating the compressor itself as the problem that needs solving, not a fixed feature of how cooling has to work. That direction matters because the demand curve behind it is only getting steeper. According to the United Nations Environment Programme's Global Cooling Watch report, global cooling demand is projected to more than triple by 2050 compared to 2022 levels, which would very nearly double the greenhouse gas emissions tied to cooling technology worldwide, even as the planet is trying to cut emissions everywhere else. Every new data center built to run artificial intelligence workloads needs cooling. Every hospital, every cold storage warehouse for food and vaccines, every home in a rapidly warming world needs cooling, more of it, more often, in more places, every single year. If nothing about the underlying technology changes, the electricity bill for simply staying cool is set to become one of the defining energy problems of the next few decades. That's the scale of problem Liebing's dissolving salt is actually being aimed at. Let's pause and restack what's actually on the table at this point, because it's easy to lose the thread in the numbers. One Chinese team has published, in a top peer-reviewed journal, a working chemical principle that cools a liquid dramatically using pressure alone, with no compressor and no traditional refrigerant gas. A second, completely separate Chinese team is chasing the same goal through electrochemistry instead. Both are responding to the same enormous worsening problem, a global cooling demand curve that standard compressor technology is increasingly unable to meet without an unsustainable energy cost. The open question now isn't whether the underlying chemistry works. The measurements say it does. The open question is, what happens between a sealed lab chamber and an actual product sitting in a warehouse, a data center, or eventually a kitchen? There's also a question worth sitting with here because it cuts against how neatly a headline like "Replace the refrigerator forever" wants to wrap up. Right now, this technology's first realistic target isn't your kitchen. The Nature paper specifically points toward large-scale industrial applications first, especially cooling systems for data centers, the enormous server farms that already run hot around the clock and would benefit enormously from a cooling method that doesn't rely on mechanical compressors prone to wear, noise, and maintenance. Failure. Data centers are simpler environments to redesign around a genuinely new cooling principle than a home appliance that needs to survive a decade of daily use, temperature swings, and manufacturing at a price point ordinary households can afford. Industrial buyers can also tolerate a higher upfront cost for a system that saves money on electricity and maintenance over years of operation, in a way an average household shopping for a fridge simply can't. That makes data centers and cold storage warehouses the far more likely first home for this technology, with consumer kitchens realistically further down the road, once the engineering has been proven at scale and the manufacturing costs have come down. Let's be honest and specific about exactly what has and hasn't been proven here, because that distinction matters enormously for a discovery this early. What's been established and independently verified through peer review is the core physical effect itself. This specific salt, in this specific solution, genuinely does absorb and release large, measurable amounts of heat through pressure-driven dissolution and crystallization, repeatedly, with real numbers behind the temperature swings involved. What's still simulation, rather than hardware, is the full working cooling system built around that effect. The 67 joules per gram figure and the 77% efficiency estimate both come from the team's simulated four-step cycle, pressurizing for heating, releasing heat to the environment, depressurizing for cooling, then delivering that cooling capacity, not from a finished appliance running in a real room for months at a time. Simulations built on solid, measured data are genuinely meaningful, and they're usually the necessary step before real hardware gets built. But a simulation is not yet a fridge sitting in someone's kitchen, and nobody involved in this research has claimed otherwise. Questions that any real product still has to answer remain genuinely open. And this early in the process, that's exactly what you'd expect, rather than a red flag. Corrosion resistance matters enormously, since a system cycling a salt solution under repeated pressure for years needs materials that won't degrade or leak. The cost of manufacturing at consumer scale is unknown, since a lab-proven chemical effect and a mass-produced, affordable appliance are two very different engineering problems with very different price tags. Long-term stability of the solution itself, whether repeated cycling for a decade changes its chemistry or its performance, hasn't been tested outside the timescales described in this one paper. And safety around a pressurized system sitting in an ordinary home, rather than a monitored industrial facility, is the kind of question regulators and engineers still need to work through before this ever reaches a consumer product. None of these are reasons to dismiss the discovery. They're simply the honest list of what peer-reviewed and published does not yet mean, which is ready to install. So did China invent something that could replace the refrigerator forever? The honest answer sits somewhere between the hype and dismissal. Nobody has built a working refrigerator using this technology yet, and anyone claiming otherwise is getting ahead of the actual published science. What has genuinely happened is arguably more important than a single finished product. A peer-reviewed, independently verified discovery has solved the exact problem that stopped solid-state cooling from becoming commercially viable for years. The problem of moving heat efficiently through a real, usable medium. That's not a marketing claim. That's a material science bottleneck cleared in a journal that doesn't let claims like that through without real scrutiny. The compressor's century-long monopoly on how the world stays cool isn't over yet, but for the first time in a long time, it has a serious, published, peer-reviewed rival standing in the room with real numbers behind it. It's worth remembering how many technologies that eventually reshaped daily life started out exactly this way, as a strange, promising lab result years before anyone could buy the finished product. The compressor refrigerator itself took decades to go from an experimental novelty to a fixture in nearly every kitchen on Earth, refined and re-engineered generation after generation, before it became the quiet, humming appliance people now barely think twice about. Solid-state lighting, the LED bulbs now standard in most homes, spent years as a laboratory curiosity too expensive and too dim to matter before manufacturing costs finally caught up with the physics. There's no guarantee Liebig's dissolving salt follows that same path to your kitchen. But the pattern of how genuinely disruptive cooling and lighting technologies have historically moved from a published paper to a household object gives some real sense of the timeline a discovery like this usually needs, typically measured in years of engineering work, not months. Picture that sealed chamber again, the one with the clear liquid and the crystals blinking in and out of existence under pressure. That small loop of salt water in a lab in northeast China isn't cooling anyone's food yet, but it's already doing something. The compressor humming behind your refrigerator right now has never had to prove it can do. Work efficiently, work without mechanical wear, and work without a drop of the refrigerant gas that's been quietly warming the planet every time a seal wears out and leaks. The next several years will decide whether that small chamber scales up into something sitting in data centers, then warehouses, then eventually kitchens. Nobody knows exactly how long that path takes. But for the first time since your grandparents' generation first heard the hum of a compressor kick on, the technology that might one day replace it has a name, a published number, and a research team racing to build the next version of it. Tell me in the comments which number actually got you. The 30-degree temperature drop in 20 seconds, or the 20% of an entire country's electricity spent just keeping things cold.